Morning, everybody. The first lesson that we're going to cover in permutations and combinations is the fundamental counting principle. And before we start, what I want you to do at the very top of your note, I want you to write this question down. How many choices do I have at each stage? And this question is going to be super, super important to you because it's one of those questions that you're going to ask yourself continually as you're doing the problems. Now, let me show you how this works. Let's take a look at the first example. Breakfast choices are pancakes or waffles in either blueberry, strawberry, or plain. How many different breakfasts could there be? Well, think about it sort of as an analogy. I go into the cafeteria one morning, Carol's in there, and I hadn't eaten any breakfast, so I want to order something. And she says to me, geez, Jody, sorry, we're cleaning up the caf today. We're only offering pancakes or waffles, nothing else. And then she says, but I can get you some blueberry topping or strawberry topping, or you can just have them plain if you want. So if you think about it from my perspective, I actually have two choices. My first choice is the type of breakfast. Do I want pancakes or waffles? And I actually have two choices, pancakes or waffles. For my second choice, I can either choose strawberry, blueberry, or plain. So for my second choice, I actually have three choices. Strawberry pancakes, blueberry pancakes, or plain pancakes. So in terms of the outcomes, which represent the type of breakfast that Carol is going to serve me, I could have strawberry pancakes, blueberry pancakes, or plain pancakes. I could have strawberry waffles, blueberry waffles, or plain waffles. So in terms of how many different breakfasts could there be, there's 6 different breakfasts that are available to me. The 6 different breakfasts that I'm looking at as my outcomes. Now, I could look at this a little bit more mathematically rather than looking at the tree diagram, and I could say to myself, okay, well, for my first decision, what type of breakfast, I had 2 choices. For my second decision, which was did I want some sort of flavor on them, I had 3 choices. If I take those 2 numbers and I multiply my decisions, or how many choices rather, that I have at each decision-making stage, 2 choices at this decision-making stage, 3 choices at this decision-making stage, I get the beautiful 6 outcomes, or 6 breakfasts. This is the fundamental counting principle. How many choices do you have at this stage? How many choices do you have at this stage? Multiplying gives you your outcome. Let's take a look at the next example. A young couple is going to have a baby boy. They have decided that the first name will come from the mom's side of the family, and that the middle name will come from the dad's side of the family. The names that they have selected are as follows. First name. So that's their first decision that they're going to make. Alex, Bart, or Chris. So the first decision that they're going to make, they've got 3 choices. The middle name, which will be their second decision, they've decided David or Edward. David or Edward. David or Edward. So in terms of the child's official name, how many outcomes do they have? Alex David, that's one possible name. Alex Edward, that's a second name. Bart David, that's a third possible name. Bart Edward. Chris David, or Chris Edward. So how many possible different names? 6 different names. Again, if I really didn't want to do the tree diagram, I could say to myself, okay, well, they had 3 choices for the first name and 2 choices for the second name. That gives them a total of 6 possible names or choices that they have available for their child's name. Let's continue with this example. Just take it one more level. What if the couple wants a second middle name of either Felix or Gibson? So that means they have a first name, a middle name, and a second middle name. Okay, let's draw it out. First name, Alex, Bart, or Chris. 3 choices. Second name, David or Edward. David or Edward. David or Edward. Now, the second middle name, Felix or Gibson. 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 So hold on, let's go back to this for 1 second. First name, 3 choices. Actually, let's call this middle name. Middle name, 2 choices. Second middle name, 2 choices. Now, right away from this example, you can see how the tree diagram is getting too big. It's getting too cumbersome. Because now, in terms of how many possible names are available, let's take a look from the tree diagram. Alex David Felix. Alex David Gibson. Alex Edward Felix. Alex Edward Gibson. Bart David Felix. Bart David Gibson. Bart Edward Felix. Bart Edward Gibson. Chris David Felix. Chris David Gibson. Chris Edward Felix. Chris Edward Gibson. So how many possible names are available for this child? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And let's take a look at the number of choices at each decision-making stage. First name, 3 choices. Middle name, 2 choices. Second middle name, 2 choices. 3 times 2 is 6. Times 2, 12 names. So some of the questions will lead themselves beautifully to a tree diagram. Some of them will get too big that they almost lead you that you want to use the fundamental accounting principle formula. Okay? Now, with regards to testing and assignments, you'll be expected to know how to do both, to use the formula and draw tree diagrams. Okay, let's flip to the next handout. The next handout sort of has some just general theory up at the top, everything that we've been talking about. It says 2 actions, M and N, can be performed one after the other. What this means is in succession. When you are performing an action or doing something, one thing in front of the other, so I'm picking a breakfast, then I'm picking a flavor. I'm picking the first name, then I'm picking the second name, then I'm picking a second middle name. That's what we call one after the other or in succession. We multiply the number of choices at each of those stages. And this is what you've just seen beautifully in the last couple examples. Now, let's take a look at another example. And this pertains to our uniform at ND. It says, examine the uniform choices at ND to determine how many different ways you can actually wear the uniform. Okay, so let's break this in half. Let's call this side boys and this side girls. Well, let's think about the boys' uniform on the bottom, what they can wear on the bottom. They can wear pants or shorts. So for the boys' bottom wear, they've got two choices. On top, let's think about this. They could wear the polo, long sleeve Oxford, or short sleeve Oxford. Polo, long sleeve, short sleeve. They've got three choices. What about on their feet? They could wear blue socks or black socks. I know most of you wear white, but technically it should be blue or black. I'm sure you're starting to see how the tree diagram is just getting insane at this point as well. Now, what about outerwear? So in the fall and the winter outerwear, we've got the vest, we've got the cardigan, we've got just a regular pullover sweater, we've got the fleecy, and for grade 12s we've got the hoodie, and we technically have the blazer if you so chose. So technically, outerwear, there's 6 different options. Again, it's really crystal clear to see that the tree diagram is not the way to go on this question. The way to go is to look at how many choices do I have on bottom, times how many choices do I have for the top, times how many choices do I have for, like, my socks, times how many choices do I have for outerwear. So technically, if we looked at this, 6 times 2 is 12, times 6, there's 72 different ways that the boys could technically wear their uniform if they owned one piece of clothing of all of these options. So 1 pair of pants, 1 set of shorts, a polo, a long sleeve, a short sleeve, a blue pair of socks, a black pair of socks, a vest, a cardigan, a pullover, a fleece, a hoodie, and a blazer. They could go 72 different days in a different outfit. Obviously assuming that they're laundering every single night. Now, let's take a look at how that changes for the girls. Well, on the bottom for the girls obviously have pants. They also have shorts, and they also have the skirt. So right away, the girls' options have increased. In terms of the top, the girls have the 3/4 shirt, the long sleeve shirt, the short sleeve shirt, and they've got the polo. In terms of, let's say, on their feet, the girls have a ton of different options, okay? Blue socks, blue tights, black tights, white socks. And again, in terms of outerwear, the girls again have vest, cardigan, pullover, fleece, hoodie, blazer. So right away, I hope you're noticing that the girls' options are huge. 3 choices on the bottom, times 4 choices for the top, times 5 choices for their feet, times 6 choices on the outer. So 12 times 5 is 60. 60 times 6. The girls could technically wear their uniform 360 different ways if they had one piece of one piece of each of these pieces of the uniform. Again, the reason that I chose this particular example is to show you that sometimes the tree diagram is not the best way to go. The formula is the best way to go. Okay, let's take a look at another example. If you toss 3 coins, what are the number of possible different results? Okay, let's think about it. Coin number 1, coin number 2, coin number 3. Well, if I have a coin in my hand, you can envision it. How many choices do I have if I flip that thing? Heads or tails? So I technically have 2 choices. If I have a second coin in my hand, how many choices? Heads or tails? 2 choices again for the second coin. If I have a third coin in my hand, again, 2 choices. So for each coin, coin number 1, 2 choices, coin number 2, 2 choices, coin number 3, 2 choices. So in terms of the possible number of different results, my outcomes, think about what my outcomes would be. Heads, heads, heads. Heads, tails. Sorry, heads, heads, tails. Heads, tails, heads. Heads, tails, tails. So heads, heads, heads. Heads, heads, tails. Heads, tails, heads. Heads, tails, tails. I could also have tails, heads, heads. Tails, heads, tails. Tails, tails, heads. And tails, tails, tails. So therefore, how many possible results? I've got 8 possible results. Now let's look at it from the number of choices. How many choices for coin 1? How many choices for coin 2? How many choices for coin 3? 8. Now, let's make it a little bit tougher. What if I had 8 coins that I was tossing? There would be no possible way that I'd want to do a tree diagram. I couldn't draw this for 8 coins. I barely kept it on the page with 3. So let's think about it. Here's coin number 1. Here's coin 2, 3, 4, 5, 6, 7, and 8. How many choices? 2. How many choices? 2. How many choices? 2. Heads or tails? Heads or tails? Heads or tails? 2, 2, 2, and 2. So each coin has 2 choices, heads or tails. How many different outcomes could I end up with? 2 times 2 times 2 times 2 times 2 times 2 times 2. 2 to the 8, 256. Okay, let's take a look at another one. You buy a new bike lock. It has 4 dials on it. You can envision, one of those locks with the 4 dials. Each of which has the numbers 1 to 8. So let's kind of envision, here's dial 1, here's dial 2, here's dial 3, here's dial 4. How many choices do I have available to me for the first dial? The first dial. I've got 8. 1, 2, 3, 4, 5, 6, 7, 8. How many choices do I have available on the second dial? 8. 1, 2, 3, 4, 5, 6, 7, 8. How many choices do I have on the third dial? 8. And how many choices on the fourth dial? 8. So how many possible different combinations could we have? 8 times 8 times 8 times 8, 4,096. This is the fundamental counting principle. Okay, let's keep going, guys. Example number 6. If I say to you, pick a red card from the deck, how many different ways could you do that? Well, I think we should maybe talk for a minute about a card deck. Because some people are familiar with cards and some people aren't. There's 52 cards in a deck. 26 of them are red, 26 of them are black. There are 4 suits in a deck. There's hearts, and there's 13 of them. There's diamonds, and there's 13 of them. There's clubs, and there's spades. Spades are 13, clubs are 13. So 13, 13, 13, 13 adds up to 52. 26 and 26 adds up to 52. But that's how a card deck is sort of divided up. So if I took a deck of cards and fanned it out in front of you and I said, geez, how many different ways could you pick a red card? Well, that would be 26, because there's 26 red cards. How many different ways could you pick a spade? That would be 13, because there's 13 spades in a deck. How many different ways could you pick a queen? Let's think about this one. Hold on, let's think about this one. There's the Queen of Hearts. There's the Queen of Diamonds. There's the Queen of Clubs. And there's the Queen of Spades. 4 queens. How many different ways could you pick a king or a queen? Key word right here. You know how little words mean a lot in data? That's a key word. A king or a queen. Well, 4 ways to pick a king. King of Hearts, King of Diamonds, King of Clubs, King of Spades. 4 ways to pick a queen. Queen of Hearts, Queen of Diamonds, Queen of Spades, Queen of Clubs. And see this little word right here? That little word? That little word means add. 8 different ways to pick a king or a queen. All right, let's keep going. How many different ways could you pick a jack or a diamond from the deck? Okay, so hold on. A jack or a diamond, with me understanding that the word or means add. Well, a jack, Jack of Hearts, Jack of Clubs, Jack of Spades, Jack of Diamonds. A diamond, let's think about it. There's Ace of Diamonds, 2 of Diamonds, 3 of Diamonds, 4 of Diamonds, 5 of Diamonds, 6 of Diamonds, 7 of Diamonds, 8 of Diamonds, 9 diamonds, 10 diamonds, Jack of Diamonds, Queen of Diamonds, King of Diamonds. Now, I don't know if you heard in me listing off all the options that, guess what? We've got a little bit of what we call overlap in that answer of 17. Because you've got the jack being considered here, and then you've got also the Jack of Diamonds being considered here. So it's been counted twice. So you're going to remove that overlap. And how many options for a jack or a diamond? 16. Jack of Diamonds was being counted first as a jack, and then we counted it a second time as a diamond. So we had to remove that overlap. Take a second and look at the next one. How many ways could you pick a black card or a 7? A black card. Okay, well, up at the top, black cards are 26. 7s, there's 7 of hearts, 7 of spades, 7 of clubs, 7 of diamonds. But before I can just leave that answer of 30, I have to ask myself, am I double counting anything? Is there any overlap in that answer of 30? Am I counting anything as a black card and then also counting it as a 7? Sure I am. 7 of spades is being counted as black and as a 7. And so is 7 of clubs being counted as a black card, because clubs are black, and also being counted as a 7. So we have to be real careful when you're using that or that you're looking for anything that might be, double counted per se. And this is what we're leading into what they call the rule of sum. Let me read it to you. It says, if one selection can be made m ways and a second selection can be made n ways, then there are m and n ways in which each selection can be made. So if there's 4 ways to select a king, and there's 4 ways to select a queen, then I'm going to add the options. So what's coming out of this is that when you see the word or, you know that you're adding. When you see the word and, you know that you're multiplying. Let's keep going. During a silent reading, a student goes to the front of the class and picks something to read from 20 magazines and 35 books. They want to select both a book and a magazine. How many different combinations of reading materials might they select? So envision that I have a big basket up at the front of the classroom, and inside the basket I've got 20 magazines and 35 books. And somebody comes up to the front with the intention that they want to walk back to their desk with a magazine and a book. So with this situation, you're making 2 choices. You're first choosing your magazine, of which you have 20 choices, and then you're choosing your book, of which you have 30 choices. This isn't an either or though. You're not going back to your desk with just one thing. You're going back with a magazine and a book. Decisions being made in succession. 700 different ways that would be possible. Look at the difference in the wording in part B. If a student wanted to pick just one thing to read, just one thing. So they walk up to the basket, there's magazines in it, there's books in it, but they just want to walk back to their desk with one item. So they're going to choose a book or a magazine. Notice the difference. They're going to choose a book or a magazine. So 20 magazines to choose from, 35 books to choose from, but the or implies they're only walking back to their desk with one item. Very, very, very important. The difference between and or in this particular unit. Okay, we're almost there, guys. There's a jar of coins. 4 pennies, 8 nickels, 11 dimes, and 5 quarters. How many different ways could you select a penny? How many different ways could you select a penny? 4 ways. Why? Because there's 4 pennies. How many different ways could you select a silver coin? Well, nickels are silver, dimes are silver, and so are quarters. 24 ways. How many different ways could you select a nickel or a quarter? A nickel or a quarter? Well, 8 nickels, 5 quarters, or means add, and no overlap. A nickel can't be a quarter, and a quarter can't be a nickel. 13 ways. Okay. So what you're seeing is you're seeing 2 neat concepts, or and and. Let's finish it off with our last example. A box contains 10 items. I'm going to highlight all the red stuff in orange. A red ball, a blue shoe, a red yo-yo, a blue gumball, a blue brush, a red hat, a red glove, a red helmet, a blue Hot Wheel, and a red kite. So all of my red items I'm highlighting in the orange there. All of my blue I'm going to highlight in the green, just so I can keep track. Okay. How many ways could you select a red object? Well, there's a ball, a red yo-yo, a red hat, a red glove, a red helmet, and a red kite. 6 ways. 6 different red things. How many different ways could you select something that's round or blue? And I think we all get the idea that the word or means add. So let's talk about what would constitute as round. A ball would be round. A shoe wouldn't. A yo-yo would be round. A gumball would be round. A brush wouldn't. A hat wouldn't. A glove wouldn't. A helmet wouldn't. A Hot Wheel wouldn't. And a kite wouldn't. So round, we have the ball, the yo-yo, and the gumball. Now, what about blue? 1, 2, 3, 4. 4 blue items. A shoe, a gumball, a brush, and a Hot Wheel car. But is there anything that's overlapping? Is there anything that's around that's also blue? Was there anything that we considered that was round? Well, we considered the ball round, the yo-yo round. Yes, we did. The blue gumball. So the blue gumball has officially been counted twice. It's been counted as round and counted as blue. Okay, let's keep it going. How many different ways could you select a toy or something red? Again, I think everybody understands the or. Now, let's think about what would fall under the category of toy. A ball would, not a shoe. A yo-yo would, not a gumball, not a brush, not a hat. A glove would, it could be a red baseball glove. A Hot Wheel car. And a kite. Would that be okay? A red ball, a red yo-yo. Let's keep the glove like a mitten. We'll pretend that this is a mitten. So, the red ball, the red yo-yo, the blue Hot Wheel, and the red kite. Those are all toys. Okay, what falls under the category of red? Well, 1, 2, 3, 4, 5, 6 red items. Now you got to ask yourself, well, wait a minute. Is there anything that we counted as red that we're also counting as a toy? Is there anything that we counted as a toy that we also counted as red? Sure. The red ball we counted as a toy, and the red yo-yo we counted as the toy, and the red kite we also counted as the toy. So technically, there are 3 things that are overlapping. The red kite was counted as a toy and red. The red ball was counted as a toy and red. And the red yo-yo was counted twice. So we had 3 items that were overlapped. Take a look at the last one. How many different ways could you select something red and then select something blue? Notice the difference in the wording. We're selecting something red and then something blue. This is decisions being made in succession. How many choices do I have available to me for red items? How many choices do I have available to me for blue items? And 24 ways. And that's it, guys. This is the end of our note. Hope that it's helpful. Please don't hesitate to send me any questions. Thank you.